Welcome to the Scanning Probe Microscopy Laboratory at INRIM. At the heart of this lab there is our atomic force and magnetic force microscope. It is a commercial setup with a fully non-magnetic head and scanner that allows performing excellent magnetic characterizations. It is equipped with a custom-built electromagnet, allowing investigations under the application of a magnetic field. All the action takes place inside the AFM head, where the sample, the tip, and the tiny laser spot dance together. At its heart, an AFM recalls an old-fashioned record player. In a turntable, a disc rotates under the pickup, and the asperities in the groove induce a movement in the pickup that is transformed into electricity and then into sound. In an AFM, the pickup is replaced by a tip that is mounted at the edge of a flexible cantilever made of silicon or silicon oxide. Instead of having a record turning, in an AFM, the sample is moved by means of piezoelectric actuators, resulting in the tip scanning the sample surface. A laser beam hits the top surface of the cantilever and is reflected onto a position-sensitive photodetector. When the tip encounters a feature on the surface of the sample, the spot of the reflected laser beam moves away from the center of the photodetector. A high-speed feedback loop moves the sample up or down, restoring the position of the laser spot at the center of the photodiode. The vertical displacement of the sample required to restore the initial position of the laser spot is equal to the height of the feature on the sample surface. By scanning the sample under the tip, a three-dimensional map of its morphology can be acquired. In this way, resolutions better than a single atomic layer can be achieved along the vertical, the Z direction. On the X and Y plane, the resolution depends on the size of the tip, whose radius can be of the order of even just a few nanometers. Even though spectacular, the ability of an AFM to acquire three-dimensional maps of the surface of samples is just the beginning. A number of physical properties of the sample can be measured by actuating the cantilever, for example putting it into oscillation close to its resonant frequency, or by coating the tip with appropriate materials. In this way, friction, mechanical properties, adhesion forces, distribution of electric charges on the surface of the sample, surface potential, and other properties as well can be measured with a properly equipped AFM. The magnetic field gradients generated by the magnetization at the surface of the sample affect the dynamics of the magnetically coated tip and cantilever, allowing the reconstruction of the domain pattern. If you take care that your microscope has no magnetic components, you can then apply a magnetic field and induce a variation in the magnetic configuration of the sample. You can even synchronize the magnetic field to the scanning of the tip on the sample surface. In this way, you collect a single image that represents the whole evolution of the domain pattern of the sample as a function of the applied magnetic field along a given profile. Thank you and take care. If you have any questions, please drop us a line.